and the Solar System 4. So our first talk will be by Vaibhav Pant on how does transverse MHD wave driven turbulence influence the density filling factor in the solar corona. So this is 30 minutes talk. So Vaibhav, I'll give you warning after you complete 20 minutes.
Okay. Can you hear me?
Yeah.
Okay, yeah, fine. Thank you, Bidya. So shall I start?
Yeah, please start. Thank you.
Okay, yeah. Good evening, everyone. First of all, I would like to thank organizer for giving me opportunity to present my work. And today I will talk about the transverse MHD wave-driven models and how does these the transverse MHD waves influence the density filling factor in the solar corona. Basically, how they influence the density of the solar corona. That's what I will discuss today. But before going into that, I will briefly introduce the history of transverse MHD waves in the solar atmosphere, just for the sake of completeness. So the waves have been discovered long back by Elephant, but then the indirect signature of waves starts coming after the launch of Skylab in early 1970s. And then later on in early 1990s, people had started, I hope you can see my cursor. So people have started obtaining non-thermal line widths, and they found that these non-thermal line widths increases as one goes away from the solar limb, or they move up in the solar atmosphere. So here we can clearly see the increase in non-thermal line widths, and then they flattens off. So several authors said that these are the indirect signatures of Elephant waves, because if there are Elephant waves and they are emitting spectra at every instant, and we are not able to resolve these spectra in time, then what we will see is a broadened spectra, and this line broadening, other than the thermal line broadening, is the manifestation of the existence of Elephant waves in the solar corona, and several people have worked on it. But then, in addition to these indirect signatures, there are also direct signatures. Why I say that direct signatures? Because then here one can measure directly measure the displacement and velocity amplitude. For example, in this movie, if I play, so we can see a system of coronal loops here. This is the active region, and then suddenly one can see these transverse oscillations after the flare. So such type of waves are known as kink waves, and since there is a direct observation of displacements as well as velocity amplitude, we call them as direct signatures. And of course, direct signatures followed indirect signatures because the imaging instrument was launched later, and then it become very popular. I mean, everyone started finding these direct signature of kink waves all over the solar atmosphere. So why do we worry about these waves? The main important point is to solve the coronal heating, and I think every solar physicist wants to solve coronal heating, and that's why people started measuring wave energy flux carried by these waves in the solar atmosphere. Now, since there were two different ways of observing, one is indirect and one is direct, so then wave energy flux can also be estimated using indirect observation as well as direct observation. So in indirect observation, we measure non-thermal line widths, right? So this is these are non-thermal line widths. And then somehow people derived a relation between non-thermal line widths and wave amplitude. And they said that, okay, there is some relation between them. And then once you know the wave amplitude from non-thermal line widths, you can derive the wave energy flux. But it's important to note that this energy flux is for the classic or bulk Elephant waves. It is for the infinite homogeneous medium, and homogeneous is important here because when you say that it is homogeneous, it means that plasma is uniformly filled. I mean, the space is uniformly filled with a plasma. So, when these are some of the recent observations by ICE instrument, and they have also seen a similar thing that the non-thermal line width, which is converted to effective velocity, increases and then flattens off. So what they did is they try to find this, they try to fit these observation with this theoretical curve here. So you know that Elephant velocity depends on the magnetic field and density. And so if you assume that the energy remain conserved when the wave propagate outward, then one can estimate that non-thermal line widths or these wave amplitudes varies as density to the power 1/4. And these curves are shown here because this is a distance from sun center. So basically it is moving up in the solar atmosphere, and you see that the wave amplitude should have increased, but observations have said that, observations reveal that they are not increasing beyond 1.15 solar R0. So then people said that, okay, if wave amplitudes are not increasing, then it means that these are the signatures of damping. And therefore they said that, okay, if one can compute the amount of this difference in energy flux, then one can compute the wave energy flux, and they said that, okay, it is enough to heat the solar corona. But the another important point is here is WKB approximation. So what is this approximation? This says that the wavelength of wave is much less than the scale height of the solar atmosphere. So you can think of it in this way: if the scale height of solar atmosphere is 50 megameter and the wavelength of wave is much less than that, then basically the wave will see it as a piecewise homogeneous atmosphere as it moves up. So then you can apply this energy flux conservation equation. But on the other hand, if the wavelength of wave is much larger than the scale height, then within a wavelength of the wave, the atmosphere is changing. So these formulations, what you get here, these expressions are averaged over a wavelength, so these are no longer valid. So this relation is no longer valid. So such type of in such case we use something known as non-WKB approximation, and recently we have shown that in 2020 that this flattening of non-thermal line width could be due to non-WKB propagation of waves and not necessarily be due to only wave damping. Now the question is whether non-WKB propagation is applicable in solar atmosphere or not. So we know that by now we know very well that the average time period of alphen or alphenic or transverse MHD waves in solar atmosphere are around 5 minutes, right? And then you take alphen velocity, give and take something around 700 kilometers per second. So if you just multiply and calculate the wave, that is around 300 megameters, and the scale height in solar atmosphere at these temperature around 50 or 100 megameters. So you see wavelengths are much larger than the scale height. So probably WKB approximation is not a good way to estimate the energy flux, and one has to consider these non-WKB approximations. But in any case, so these expressions, whatever I have mentioned here, are valid for homogeneous plasma, and this is important. Now the question is, do we get homogeneous plasma in solar atmosphere or not? That was from the indirect observation. From direct observation, it is very easy. What we can see here is are the Doppler velocity shifts moving upward in these in coronal loops and in solar atmosphere, and they are present everywhere. Right? And then again, one use this simple formulation, like rho v square into VA. This is the expression for energy flux, and that turns out to be quite less because of the line of sight effect. But in any case, people are using these formulations here. Again, assuming that the medium is homogeneous, but indeed it is not homogeneous if you just look at this movie, because there are a lot of structuring that is already there. So then people started thinking about, or people started finding waves in the ensemble of flux tubes. That means there is no one structure, there are many structures, and also it is not homogeneous, because when you have different structure, of course, the density distribution will not be a homogeneous distribution. And this has been done some time back by several people, and they found these are the chromospheric SPQs, and you can clearly see that it's not, these are different flux tubes, right? So these are the ensemble of different flux tubes. And then interestingly, what you find is that waves are coherent over large distances. So if this speckle move in this direction, probably this speckle will also move in this direction. So they are coherent over larger scales. Similarly, this is the case here. If you look into the corona, this is the chromospheric images. These are this is the coronal image, and here also you can see that the waves are coherent over a large length scales. So what it suggests is that even though wave is moving in an inhomogeneous medium, they are still coherent. Okay, so this is the this established the wave coherency over large scales. Now the question is, if that is the case, why do we care about the ensemble of flux tube? I mean, why don't you just use the formula of the simple homogeneous medium and just compute the energy flux? to answer this question, we have to understand how the energy flux is distributed in a magnetic flux tube. So if you take if you take a flux tube, if you assume it to be like a cylinder, and I will discuss later whether it is like a cylinder or not, but if you assume it to be like a cylinder, then the kink waves, basically the transverse waves, in those waves, most of the energy flux is concentrated inside this overdense structure or inside the flux tube. And that's why these are known as the body waves, because they are concentrated inside the body of flux tube. While if you have you also have transverse wave, which are concentrated at the surface. These are known as surface Elfman waves. So from here, you can think that if you have like several flux tubes which are separated with some distances, then your energy flux, energy is not carried upward everywhere. I mean, they are only confined to these flux tubes, be it a body wave or be it a surface wave. And therefore, it is important to understand the structuring of solar corona. Or in other words, these waves can reveal about the density structuring of solar corona. And that's what we will talk about. And so this is for the single flux tube. And what happens if you have an ensemble of flux tube? And this exercise also been done sometimes back. So you take an ensemble of flux tubes with different cross section, and then you define an average cross section BF here. And you know that in the solar atmosphere we have the flux tubes of different cross sections. Then the wave energy flux depends on the spatial orientation of these overdense flux tubes. As I said, because the wave is confined to these flux tubes only. Wave energies are confined to these flux tubes. So then people derive the relation for this depending upon how much volume is occupied by these flux tubes as a fraction of the total volume. And if you assume a homogeneous medium, then you have this formula for classic and bulk Elfman waves. For kink waves, you just average over the density inside and outside. Rest of the things remain same. This is for the long wavelength kink wave. And then when you have a multi-stranded flux tube, then you end up in getting one extra factor here, F. And this is known as the filling factor. In my talk, I will call it as a filling factor. And this F is basically the density filling factor here. Filling factor could be magnetic filling factor, but here it is a density filling factor. And it is defined as the volume of loops divided by the total volume in which they are enclosed. So here it is, if you know the total volume R, and if you know the volume of individual loops, then you just divide both of them and you'll get the filling factor. From observational, it is very, very difficult to derive the filling factor because first of all, we do not know how many loops are bundled together and how to determine even that. We tried to do that in one of our paper in 2016. But I mean, there are a lot of uncertainties. But this is, I think, the first attempt where we could, we derived the filling factor for coronal loop oscillation. But nevertheless, I will discuss that this method is not correct now because the field has really advanced since then. So yeah, the first author is sitting here. So yeah, no problem. So anyway, let's move on. So let's understand what are the other ways of measuring density filling factor apart from simple imaging, where you can just measure the width of individual strand and the width of the region enclosing those individual strands. So there's other way of doing it, and that is by using the emission measure. And this has also been done a long time back. I think in 1990s also some people were looking for it. And but anyway, these authors have shown that the densities in coronal loop plumes, interplumes is not homogeneous along the line of sight. And how do they do that? They calculate the filling factor like this. They estimated the intensity that they are getting, and they divide it by the expected intensity that one should get if the coronal loop is uniformly filled with a density NE, and its depth, the depth of coronal loop is H. The question is how to find H here, right? So what people do is they found the width of coronal loop, assume a cylindrical geometry, and the width is equal to the depth. And then you know the H. NE can be computed by a line ratio method, and then you have expected intensity here. So once you have expected intensity, and if your reality match with expectation, that means filling factor is 1, everything is homogeneous. Go back to the classical Elfman wave formula that we have discussed and just use that and life will be simple. But then when the reality will not match expectation, then the problem comes. Then what should we do, and how should we estimate these filling factors? So And this is a very interesting one. In fact, this was the motivation for us to look this problem in more detail using MHD simulation. And this work was done by Gijesh Gupta. And what they have computed is, they observed a corner loop with eyes, and this is a spectral image. And then they estimated the filling factor, and they found that the filling factor is increasing with along the length of coronal loop. Somewhere here, there was a lack of data. The images were failed, I believe, and then it again decreases if it goes towards the other end. So that means the filling factor is increasing with height along the corner loop. So the question is, what can explain such a variation? There could be several reasons, right? And the most intuitive reason is expansion. So sorry for this. This is a very bad drawing. But anyway, the thing that I want to explain here is that the flux tube expands as they move up in the solar atmosphere. And if you think of if you think of a corner loop as a bundle of several strands, and these strands are expanding, naturally your filling factor will be more at larger height and less at the foot point. So this could be one of the reason for the increase of filling factor along the corner loop. But the problem is that the rapid expansion of flux tube happens while moving from chromosphere to corona. If you are only confined to corona, then whether the expansion is that it can explain the increase in filling factor from 0.2 to 1 is something that needs to be discussed. Okay, so that is one thing, and we will see from our simulation we have calculated the filling factor increase due to this expansion. We will talk about it later. But there is another thing that can explain this variation in, not necessarily increase, but variation in the filling factor is the multi-stranded loop geometry. So it depends on the orientation of loop and orientation of individual threads. Now, there is no reason to believe that all threads will be parallel. They will be entangled, they will be braided. And it really depends on your line of sight, the line of sight that you choose. So along some line of sight, you will have some few strands. At another line of sight, you will have more strands. And then that can also explain the increase in the filling factor, or the variation in the filling factor in solar corona. But there is a systematic increase in the filling factor from the foot point to loop top is something that we need to explain still. So we'll see how much it is valid. And the third thing is the uncertainty in the measured quantities. So measured quantities were the depth and the densities. So if there are uncertainties in the measurement of those quantities, that can also lead to the false increase. There may not be any increase, but it would be a false increase, right? So we will see how to go about it. But then that work was like a motivation for us to look this problem in more detail. So what could be the other thing that can increase the filling factor? For that, we need to go back to some of the single flux tube simulations. And these are the single flux tube simulations which are subjected to the transverse oscillation. So these loops are moving like this along X direction. And here you can see that these transverse oscillations here, these body waves are changing into the surface alpha waves because of resonant absorption. And once the velocity is only concentrated at the boundaries, these lead to the development of shear, and that lead to KHI vortices to build up, and then it will go on, and finally it will get dissipated because of viscous dissipation. So the point here is that if you look into these simulations, then these inhomogeneity layer, which is here, which is like very narrow, is now more extended here, right? So this could be one of the reason, and this could be one of the reason that why filling factor is increasing, because if you just take one line of sight here and you take a line of sight here, you will get probably extra emission from this region. So this is, no one has done this analysis. These authors have not done the analysis for filling factor, but this is my understanding. And these are known as KHI vortices rows, as so-called as quick roll. These are new names discovered, given by these authors. But another important point is, if you look at these vortices as a function of height, so this is the loop foot point, this is the loop top. So you see that these vortices are clearly more at the loop top compared to the loop foot point. And the reason is that because these loops are line tied, okay, and these are the fundamental, the oscillations are the fundamental oscillation, and fundamental oscillation has nodes at foot points, while the velocity is maximum at the loop top, and therefore the shear velocity will be maximum at the loop top than at the foot point, and therefore you have more vortices at the, KHI will develop faster at the loop top than the loop foot point. And from here one can clearly see the dependence of turbulence over height. And probably if this is responsible for filling factor, then probably the filling factor will also increase. But we'll see what happens. Then
you have
then
taken
comes the
20 minutes.
sorry.
You have taken 20 minutes.
Okay, so I have 5 minutes more, right?
Yeah.
Okay, so then comes the multi-stranded loop oscillations, and here people have started with a multi-stranded loop, and then they excited transverse oscillation, and they found that the structure of loop is completely destroyed after some time, because of the development of these vortices and turbulence. And so the question is, even if you start with these parallel multi-stranded loop, you will not even left with any loop-like structure. So it's all the turbulent plasma here. So the question is, what will be the filling factor here? And these authors have estimated emission measure, and they found that
Yeah, I think. Okay.
screen share है. तो वहाँ से बंद करो. Hello, Bidya, can you hear us?
Yes. You need to share.
Yeah, you need to share, right?
Yeah.
So there was a technical glitch here. Sorry. अरे Ram.
इसको रिवेस कर बैक पीछे
ये कहाँ है?
इसका जूम पूरा इससे ऐसा आएगा यहाँ से इधर एक मिनट रुकिए ये वाला ऑप्शन जो आ रहा है
नहीं आ रहा.
देखिए ये वाला ग्रीन बट इससे होगा
Share screen entire screen. Okay, can you see the screen now?
Yes.
Okay, fine. Yeah. So sorry for the glitch. Yeah, it's okay. I will do that. So I will now quickly wrap it up. Yeah. So this is motivated. This type of setup is motivated from the observations, and then we excited transverse MHD wave at one base of at the inner boundary of the simulation, and these waves will move up and displace the corona, displace these flux tube transversely. So here is one movie. So this is at the middle of these at the middle of the simulation tube, and here you can see the generation of the turbulence. And these are the velocity vectors. And now question is, how does this turbulence changes the density structure of solar corona? So what we did is we put a contour over these density enhanced structure at time t equal to 0 at different heights. This is at the loop bottom, this is at the loop top. And remember, I said that one mechanism of increasing filling factor is the expansion of the flux tubes, and there is indeed an expansion of the flux tube, but there is not very much increase in the filling factor. However, at the later time when turbulence developed, of course the instability is also developed here, but they are more at the loop top than at the loop
think again there's a problem.
Yeah, the screen is frozen.
Screen is frozen, yeah. Whenever this thing happens, I check my network first.
Hello, can you hear me?
Yes.
I don't know what's happening. Sorry. Yeah, so I will again start from here. Yeah. So we found that the filling factor is increasing, and this increase is not because of the expansion. Because of the expansion, there is a very little increase, but the most of the increase in filling factor comes through the development of these turbulence. Yeah, so that's what I have mentioned here. So I will just quickly go towards the towards the conclusion. But the problem here in this method is that we do not have a density estimate using remote sensing instrument. So here we are directly capturing the density, right? Density because those contours were enclosing density. So this is the density filling factor, but that's not what we measure from observation. From observation, we measure something known as the emission from the plasma. So we have to do the forward modeling for one of the emission lines. So we chose the iron 13 emission lines. And this is how it looks. So even though you have a development of turbulence, you do see coronal, you do see strand-like structures here. That means there are no real cylindrical structures, just turbulent plasma. Because when you forward model it and you integrate it along the line of sight, this turbulence plasma will give you an impression of strand-like features. And then what we did, we also degraded the intensity to the, degraded the resolution to the ice. And then you can see that it smooths out. And then we use the same analysis as an observer would have done. They would have computed the depth of the coronal or depth of these structures as the width of these structures. That's what we did. For example, we just plot the cross-sectional intensity and calculate the FWHM in both the cases. So this was taken as the H, which is the depth. And the density is estimated using line ratio, simple. And then what we did, we matched with what we get intensity from the synthetic spectra using forward modeling. And this is something that we computed using line ratio technique, as well as computed by putting some value of depth by calculating the FWHM of the width of the structures. So then what we find is that using forward modeling, the filling factor indeed increases, but the increase is not smooth, as in the case of when you have a simulation data. And these bumps here are coming because of the line of sight effects. At some for some line of sights, you have more strands along your line of sight and less strands along less strand in other line of sight, and that's why you get these differences in the filling factor here. But overall, the increase in the filling factor along height is seen in forward model images. So what we have learned from here is that the filling factor, the method that we have been using to compute the filling factor using this reality versus expected ratio, this may not be a very good representation because there are a lot of line of sight effects. And this, I believe that once your the spatial resolution will improve, then it will become even more worse. That is the point, because when the spatial resolution will improve, then you will go to this limit. Then you will go to this limit from here to here, from the bottom panel to top panel. In top panel, it is even worse because the height, if you measure it using the width of these structure, then the width seems to be very little. But along the line of sight, the widths are very large because these are not the real loops. These are not the cylindrical structure. These are just the turbulent plasma, which is integrated along the line of sight. So that is the problem here. So probably this is not a very good method to estimate the filling factor. And I do not know any other method better than this anyway. So the last conclusion here is that these wave turbulence model affect the density structuring of solar corona, and they are also able to explain the observed increase in the filling factor. These simulations are for the open loops, but for the closed loop will also show a similar behavior, with a difference that the filling factor increases more steeply with time, and that is the only difference I think will be there. The important caveat is that these are ideal simulation, need to incorporate thermal conduction and radiative losses. We didn't do that because it was easy to perform simulation without these energy loss or transport mechanism. And then I leave you with this very new simulations which were published in very recently. And there you can see these are the line of sight averaged images here in this plane, and you see beautiful coronal loops here. And as I will play the movie, you will see in the right panel, this is the cross-sectional image. I mean, this image, the plane is obtained by the averaging over line of sight like this along Y. So you will see that though you see coronal loops here, there are no coronal loops here. So let me move on. And then you see that as it is moving towards the loop top, the structures are become more turbulent, and there are no coronal loops here. So basically, it is just a line of sight effect. And that was also, I mean, these are very good simulations, but this was also implicated from our and the simulations that were done before. So this raises question about the wave models that were constructed assuming cylinders. But I still believe that they are still applicable because if you want to know my personal opinion, that is, if the displacement of the loops are much larger than this inhomogeneity length scale, then wave really doesn't care about these small scale inhomogeneity. And that's why probably this is one of the reasons why these single loop models that were constructed are so good in explaining the features. However, over a final scales, there are only turbulent structure and probably no cylindrical structures in the solar corona. Okay, thank you. I will stop here.
Yeah, so I'll take questions from the in-person participants. So whoever has a question directly, please speak. Please ask the question. Vaibhav, do you see anyone has question?
Yes, we have one.
Yeah, then please take directly.
Yeah. They are going there.
Very nice talk, first of all. I have just a query. The simulations, the single span simulations that you've done, not you. Somebody else.
Somebody else has done. I have also done, but that is they are not here.
Okay, fine. So what I mean to say is that the gauge instabilities are basically velocity shear.
Shear, yes, exactly. Yeah.
But now when you have magnetic fields, okay, they will try to hold back that strand, right?
Yes, exactly.
So to start a cage, what should be the velocity shear is to magnetic field ratios?
Yeah, that is good. I think that we have not computed, but what we know is if you add a twist in the magnetic field, that will resist the formation of KHIs, and then probably you have to drive even more to develop these KHIs. So that is a good question, but we have not computed this velocity shear versus magnetic field. What would be the comparison between them? Because you rightly said that magnetic field suppress the formation of KHIs because there is a magnetic tension that will try to suppress the formation. But still, we find it here. The magnetic field are off and on. If you want the order of estimate of magnetic field in our simulation, it is around 5 Gauss. So it is around 5 Gauss, and the velocity amplitude around 15 km per second, something like that. So it was enough to form KHIs over a period of time. But if you increase the magnetic field strength, or if you add the twist, and it has been done, if you add a twist in the magnetic field, then you have another B5 component, and then it will suppress the formation of KHIs. You have to drive even longer. So I mean that's what my understanding is.
Okay. Other question from the in-person participant? If not, then I'll take a question from Dipendra. Dipendra, please unmute and ask the question. And by that time, I request the next speaker, Lakshitha Nama, please connect your presentation so that we don't.
Hey, Vaibhav, I don't know. Can you hear me?
Yes.
Yeah. So the connection is going on and off. In fact, just about when you went off, there was a big solar flare, M4.4, M4.1 class, according to the CC flare alert system. Anyway, question for you. There has been a long-standing puzzle, which to my mind has not yet been solved, which I have been discussing with various people, including Anna and Dana Longco. The conundrum is this. When you look at the corona and look at theoretical models, the theory says that the magnetic fields should essentially fill up the whole volume of the corona. However, when you look at the corona in X-rays or extreme ultraviolet, you only see certain loops lit up, whereas magnetic fields are there everywhere. Does your simulations throw any light on this very puzzling sort of phenomenon, that you only see some loops while we know that the corona is full of loops, perhaps?
Yeah, no, our simulation doesn't answer this question. This is obviously a difficult question because in our simulation, we design flux tubes on our own, right? They are not they are not appearing self-consistently from the simulation. Like you have a homogeneous plasma with homogeneous magnetic field, and then it leads to the formation of coronal loops. That is not there. But what I think is happening, there are several things that are happening apart from the waves that are traveling. These lead to the formation of a small scale structure and small scale strands. That is clear from our simulation. But in addition to that, there are also small scale reconnection that will also light up these small scale strands in an active region that will appear that will then appear as coronal loops in the images. But I think we really do not know what exactly it is. Why do only some part of magnetic field is being brightened as a coronal loop and other fields are not, because of course the field is always continuous and always permeates the solar atmosphere. Yeah, so our simulation doesn't talk about that. That is the question that probably I don't have any answer as of now.
Yeah, now I request.
Bidya, if I could just add, one point in the discussion. Dipendu, you're right. So basically, see what we see the corona is the density contrast. So how this density contrast is maintained by the magnetic field contrast also at different regions, we still do not probably understand. So it is not a uniform field which is there.
Yeah, that's what I said. I mean, small scale reconnection can also fill up the plasma and may lead to these.
So even
but we do not know.
Even further, if you look at the plume interplume structures also, we know both the regions do have magnetic field, but it's very clearly a step function kind of thing. There are boundaries. How these boundaries are maintained also for a very long period of time is a big question, particularly in the extended corona as well. Yeah, this puzzle is still open.
Yeah, so Vaibhav, thank you very much for this very informative talk. Thank you. So you can still speak, but let the next speaker to connect. Okay. Yeah. So Lakshitha Nama, please. So title of our talk is elemental abundances during A-class solar flare.
Hi everyone, my name is Lakshitha Nama. I'm a PhD student at Christ University in Bangalore. I'm working with Sudip Mandal from PRL, Dr. Shyama Narendranath from URSC, and Professor Paul Kitty from Christ University. I'll be talking about deriving elemental abundances during A-class solar flares using soft X-ray spectroscopy from Chandrayaan-2 XSM. I'll first talk about the instrument in brief before proceeding to tell how exactly I have used the data. The X-ray solar monitor on XSM on board Chandrayaan-2 measures the sun as a star in the 1 to 15 kiloelectron volt energy range, and it measures the spectrum every second with a cadence of it measures every second with an energy resolution better than 180 electron volt at 5.9 kiloelectron volt. Its dynamic range is such that it measures flux which is below A class level up to flares of up to X class level. This is currently the highest resolution spectrometer that is observing the sun in the soft X-ray energy range. Thus, we want to use this instrument to solve the anomaly of abundances that is seen in the corona, which is called as the FIP effect. What is happening is, since mass and energy transfer to the corona is coming from the lower atmospheric layers, it is natural to assume that the photo abundances in the corona and the photosphere are similar. But what is seen is that only for elements that have a first ionization potential less than 10 electron volt, their abundances are seen to be 3 to 4 times more in the corona than in the photosphere. While for those of high FIP elements, the abundances are similar to the photosphere. So in order to quantify this FIP effect, we use the term FIP bias, which is the ratio of abundance of an element in the solar corona to the abundance of the same element in the photosphere. Interestingly, it is also seen that the FIP bias is different in different regions of the corona as well. For example, in the quiet regions, the FIP bias is 1 to 2, that is, they almost retain the photospheric abundances. While in closed loops, in active regions, the FIP bias is 2 to 4, which varies depending upon the element under study also. For all the higher class of flares that have been studied till now, the FIP bias is seen to vary from 1 to 4. And it depends not only on the element that we are studying, but also on the phase of the flare that we are studying. For example, Sharma and et al. In 2020, they carried out time resolved analysis of higher class of flares using SMART-1 XSM and Chandrayaan-2 XSM also, and messenger sats. And these are the plots from that. They studied the evolution of FIP bias for low FIP elements and saw that the FIP bias is varying when the flare evolves. For example, in the pre-flare phases, the FIP bias is 3 to 4. While in the peak, it is coming down, and again during the decay phases, it is going up. Recently, Biswajit Mandal et al. 2021 also found similar variation during B-class flares using Chandrayaan-2 XSM itself. For magnesium, aluminum, silicon, and sulfur, they found that during the pre-flare phases, the abundances in the corona is 3 to 4 times higher than the photosphere, which is represented by the green bar here. While during the peak of the flare, it is coming down to near photospheric values, and again during the decay phases, it is going up. It is recovering back to the coronal FIP bias. They also found the evolution of temperature and emission measures, and they see that as the intensity of the flare increases, the temperature and emission measure is going up, reaches peak during the intensity peak, and again comes down. One very important reason why we have to study FIP effect not only of higher class of flares but also lower classes of flares is because the theories that try to explain the FIP effect also predict that the coronal heating problem and the abundances anomaly are related. So if we try to understand the FIP effect in lower classes of flares, it will help us gain insights into the coronal heating problem as well. So the questions that we're trying to answer from this study is, do the A-class flares follow the standard flare model? And what is the order of magnitude of the physical properties of the A-class flares? Are the abundances of elements in A-class flares similar to the photosphere, or is the first ionization potential effect seen here as well? We can use XSM to help solve these because XSM was operational during the solar minimum of the 25th cycle, that is during 2019 and 20. And as a result, it has observed hundreds of A-class flares. Since it provides very high resolution spectra, we can use this to derive the values of temperature, emission measure, and the abundances of various elements also. First, we have to identify the A-class flares from the light curves. So these two are the two plots on the right are representative light curves for 2 days, where we have the red shaded region shows the flare that we have taken for time integrated analysis. And we have considered all such flares from the first two observation seasons of the first observation sessions of the XSM. And the red dashes here show the peak time of all these A-class flares that we have taken. After we selected the flares, we have generated the time integrated spectrum using XSM data analysis software, and we have fitted it with a isothermal plasma assumption using CHISOTH model written by Biswajit Mandal. what the model does is it uses the Chianti atomic database to generate the synthetic spectra, and then it fits the spectrum using XSpec. The parameters that can be varied are temperature, volume emission measure, and elements whose atomic number is from 2 to 30. In the spectra, this is a representative spectra for one such flare. We have left the abundances of magnesium, aluminum, silicon, and sulfur whose emission complexes are visible in the spectra as free parameters, and also temperature and emission measure that is derived using the continuum. And here we have I have plotted all the results from a time integrated analysis. We have defined quantity called as flare number, which basically shows it varies from like all these red dots show the A1 class of flares, green shows A2, blue shows A3, and this mustard yellow is A4, and black is A6. When we plot it against temperature, we see that temperature is varying linearly with the subclass, which is also seen for higher class of flares. Also, as expected, emission measure is also scaling with the subclass of flares. When we plot the flare number versus FIP bias of magnesium, aluminum, silicon, and sulfur, we saw that all the FIP biases are near 1. That means that when we do the time integrated analysis, we do not see any FIP bias here. After this, we want to try the time resolved analysis, but it is not possible to do the similar analysis as is done for higher classes of flares, because A classes of flares have very weak signal. For this, we have tried a different method. That is, we have found flares that have similar profiles. What I mean by similar profiles is that we try to find sets of flares that have similar pre and post flare count rate, and they spend approximately equal amounts of time in their different phases. Then we have overlapped them by taking the peak time as 0. We have divided them up into multiple time bins, which are shown as the shaded red and green and yellow regions. Then we have generated spectra for each of these time bins and added the time bins of corresponding light curves, time bin of the two flares. And then we have performed 1T CHISO model analysis as explained earlier. These are results for one such set of flares. This shows that as we saw for B class of flares, the temperature is also, here also the temperature is increasing with the increasing the intensity of the flare, and during the decay phase it comes down. And so does the emission measure. While the abundances of magnesium, aluminum, silicon, and sulfur show an abundance like they show the FIP effect. That is, during the pre-flare phases, the abundances are 3 to 4 times more than the photospheric values, which are shown by the black dashed line here. And then during the peak of the phase, the abundances are coming down, and again during the decay phase, it is going up. One thing to note here is that the temperature peak is reached first, and then in the next bin the emission measure peak is reached, which is consistent with the standard flare model. Biswajit Mandal et al. 2021 have given 2 scenarios to explain what is happening in the B class of flares. Since we see a similar variation of abundances in A class flares also, we can use the same models to predict what is happening in A class flares also. The first scenario says that the heat energy that is released during magnetic reconnection travels down to the chromosphere and causes the material here to evaporate, which is the chromospheric evaporation. This is when the temperature peak is reached. Then the evaporated plasma quickly fills the coronal region, which is when we see the emission measure peak. And then when the flow slows down, the plasma gets enough time in the fractionation layer to undergo fractionation, and then quickly recovers back the coronal FIP bias. The second scenario suggests that at the onset of the flare, alpha waves are released, and these alpha waves move slowly to the chromosphere. But the heat energy which is released is transported to the chromosphere via suprathermal electrons, which causes chromospheric evaporation, and this is when the temperature peak is seen. When after this, when alpha waves reach the chromospheric layer, it causes fractionation, and this fractionated material then moves to the chromospheric coronal region, and that is when we see the coronal FIP bias, which is being recovered back. So the key points from our study is that by performing the time integrated analysis of 65 A-class flares, we have shown that during peak of the flare, the abundances of low FIP elements are nearly photospheric, and the temperature and emission measure vary as shown here. We have also carried out the time resolved analysis by adding the spectra of similar A-class flares. We have shown that the abundance of magnesium, aluminum, silicon, and sulfur evolve according to the standard flare model and the ponderomotive force model. The abundances of these elements have 3 to 4 FIP bias during pre-flare phases, and they drop to near photospheric values during the peak phase. Beyond the flare peak, the abundances are seen to get enriched again, and they recover back to the coronal FIP bias at the end of the flare.
Okay, thank you very much for this nice talk. So now we'll take some questions from, let's take questions from the in-person participant. So whoever has a question, please speak up. From online participants, I don't see any raised hand, but
Hello, Bidya.
Yeah.
I have a small question.
Yeah, please speak.
Yeah, Lakshitha, you showed a model from the Mandal et al. Paper, and they used it for B-class players. But this is kind of like a standard model where you have loop structure.
Yes.
But these A-class can happen in the braided structures also. Then how this will be applicable to that kind of scenario?
The results that we got for A-class of flares is very similar to what we have seen in B-class of flares also. So that is why I'm saying that it follows the same model.
But I think like that Parker interesting, that can also be the location of these kind of small energy signatures. So these models may not be like able to explain those scenarios.
I'm not aware of it.
You can think about some other models from your side also.
Okay, so there is a chat. Can you read the chat, or I shall read the chat? There's a question from Sankar Subramanian. Are there one-to-one correlation between OSPX and XSPEC? Is the correlation validated to compare the result from Nagendranath et al. 2020 and this, and Mandal et al. 2021? And then there's a follow-up question.
No, the duration of flares is similar.
Okay. Okay, I think you can comment also in the chat. So we should move on to the next speaker. Okay. You can continue this chat here. Okay, yeah. Thank you, Lakshitha, for this nice talk. Thank you. And now I invite Megha Anand. So she will talk on elemental abundances during magnesium to core to wing ratio and its center to limb variation in sunspot from iris. Yeah, Megha, please start. Thank you.
Yeah. Good evening, everyone. Thanks to the organizers for giving me an opportunity to present the work done at IOCA in collaboration with Professor Durgesh Tripathi and Pradeep Kashyap. So I'll be speaking about magnesium core to wing ratio. This is also known as magnesium 2 index, and its center to limb variation as seen in sunspots observed from iris. So we all know that the absorption of UV photons by the atoms and molecules in the atmosphere, Earth's atmosphere, is responsible for most of the heating in the thermosphere. And although the overall brightness of the sun varies by only 0.1% over the solar cycle, the UV flux changes by the factor from 2 to 10 across the spectrum. And it's about 30% of the atmospheric heating comes alone from helium 2304 angstrom line alone. Since the UV radiation cannot be measured from the ground, there has been different proxies developed over years. Some of them are the sunspot number, but this is least appropriate in deriving the UV irradiance. There is F10.7. This is radio 10.7 centimeter line, which forms in the transition region. There is calcium K index. Calcium 2 line forms in the chromosphere. There is helium 1 equivalent width. Helium also forms in the chromosphere, which is 10-830. But this proxy can be used only for the cooler part of the UV irradiance. And there is also Mg2 index. Magnesium also forms in the chromosphere, but a little higher up compared to the calcium, the line core, and the line wing forms deeper in the photosphere. So except for magnesium 2, all the other proxies here can be measured from the ground. If we compare the magnesium 2 line with the calcium, it's been seen that the magnesium H and K lines are better diagnostic of the higher part of the chromosphere plateau than the calcium 2. So here is the simulation from Lennartz et al. They plot the intensity of different lines shown here: magnesium 2, calcium 8542 angstrom line, and H alpha as a function of height. Here the different lines corresponds to the optical depth tau is equal to 1 from where the lines emerges. So clearly both calcium and magnesium kind of have similar structures, but magnesium forms higher up in the chromosphere compared to the calcium. It's also well known that the magnesium is about 18 times more abundant than calcium. Because of these quoted reasons, magnesium index is considered to be better correlated with chromospheric emissions than calcium K. If we compare the magnesium index with that of F10.7, averaged over 13.5 days periodicity, which is the signature of UV emissions, we see that compared to F10.7 over a certain period of years, with the magnesium index exhibits a better 13.5 periodicity compared with the F10.7. So because of these listed reasons and many more, we are interested in magnesium 2 line. So let's see what is this magnesium index and how it is defined. Here is the relative intensity, which is plotted in the 200 to 400 nanometer region. And magnesium 2 absorption line forms somewhere around 2800 angstrom. So when zoomed in, you see a broad absorption profile with magnesium H and K forming somewhere in the core like this. Since the magnesium 2 line cannot be measured from the ground, it has been found so far through the rocket and space-based instruments. So for this reason, Heath, for the first time in 1986, proposed that there should be something called magnesium 2 index. This is the ratio of line intensity to the continuum intensity. So basically, in order to eliminate the effect of wavelength-dependent instrumental drift, this concept was introduced. And so far, the magnesium index has been observed by the following experiments in which the spectral resolution is quoted here, which all have comparatively poor spectral resolution. So because of this reason, so far the magnesium index has been studied like considering the line intensities at these positions. For example, here the quoted 6, 7, and 8 positions are considered as the line position, and the weighted average of this as the line intensity. And the continuum is considered in like the positions 1 and 2 on the right hand side and 11, 12 on the left hand side. So far magnesium index has been defined like this using low spectral resolution data and also assuming sun as a star. But we know that magnesium H and K lines are optically thick lines, which has different structures like this. For example, the K3 here, magnesium K line, forms highest in the atmosphere, just a few kilometers below the transition region. But K2, V and R, which are the blue and red emission peaks, forms little lower in the chromosphere, and similarly K1s which forms further down below. So this is a very structured optically thick line. And also compared to the oscillator strength between the MGH and K line, the K line has higher oscillator strength than the H. So for further studies, I'll be picking up only magnesium K line, though the nature of both of them, like the center to variation studies, etc., are somewhat similar, just the intensity is higher for the case of magnesium K. By Kashyap et al. 2018, they also studied the importance of spectral resolution. They basically wanted to study the difference between the coronal hole and quiet sun as seen by the magnesium line. So here is the image of coronal hole and quiet sun as seen by magnesium K line core, and this is the continuum. So by just eyes, you can't differentiate between coronal hole and quiet sun. But when they did a detailed study of binning it over the magnetic field strengths, and also studying it as a function of spectral resolution, they see that at a spectral resolution of 1 angstrom, they see intensity difference between the quiet sun and the coronal hole. But this difference disappears when lower spectral resolution is considered. So this was kind of a motivation for us to study the magnesium 2 index with high resolution and also high spectral and spatial resolution, which can be provided by iris. And also we wanted to study different structures like sunspots, umbra, penumbra, quiet sun, plages. In these different structures, how does magnesium 2 index varies? Here I'll be presenting only about sunspot, umbra, and penumbra results. Since sunspot basically comprises of very small area in iris observation, we had to take a number of observations. So here is an example where we have taken 55 iris observations spanning the entire mu region. So one of the observations zoomed in would look like this. This is the iris MG2 at K line intensity. The observation looks like this. In order to separate the umbra and penumbra for our further studies, we used HMI continuum. This is the corresponding HMI continuum of this observation. So here is the iris field of view. When zoomed in, you see the umbra and penumbra in the following way. For further identifying umbra and penumbra, we used the famous intensity cutoff for the case of umbra, which is 50% of the continuum intensity, and for the penumbra between 50% and 90%. So considering this and also bringing the HMI continuum to the iris resolution, we get the image something like this. So here is the contour which corresponds to umbra and penumbra. At any point, if you would look how is the magnesium profile, for example, at the umbra, you see the magnesium profile given in the following way. So the central reversal is absent in the case of umbral magnesium profile, which is a signature of umbral profile. The magnesium line, as I said, is optically thick. It depends greatly on temperature, density, and the magnetic fields present in the line forming regions. So this is the typical umbral profile. Similarly, the penumbral profile would look something like this, which is where there is central reversal present. Since we are interested in magnesium index, we need to find the line and continuum intensity. For that purpose, we fit a single Gaussian for the case of umbra and double Gaussian for penumbra. And the area under these curves for both umbra and penumbra is considered as line intensity. And in order to obtain the continuum intensity, we get an integrated intensity in the 2830 to 2834 angstrom. Hello, am I audible?
Yeah, continue.
I see, okay. So now that the umbral and penumbral line and continuum intensities are available, we do the similar exercise for all the selected 55 observations. So here is the umbral line and continuum center to limb data. Like you see a lot of data gap because the umbra spans very small area, and below 0.2 mu, it is not possible to identify the sunspots. The similar penumbral data points spans like this. So both the umbral and penumbral data distribution shows some kind of trend. So in order to see this trend, we average it over different mu bins of mu 0.1 value. So this is the umbral line and continuum variation. We have a lot of scatter here because the statistics is not good for the case of umbra, but it is somewhat better for the case of penumbra. When you see the continuum, both umbral and penumbral center to limb variation shows the typical limb darkening which is expected for this line. But in the case of line core, we are yet to interpret this result. And also because of the poor statistics, we don't know whether this is a raise or what exactly is the trend. The trend can also be like this. Now that the line and the continuum values available, we get the magnesium index for both the umbra and penumbra. So far we just have one single value of magnesium index over that particular day with the poor spectral resolution. But now we have the center to limb variation, and it definitely has a trend where the magnesium index varies at each mu. Similar studies have also been done for the case of Quaitson and Plages by Pradeep Kashyap, and we are in the process of interpreting the results. So we have presented the spatially and spectrally resolved magnesium to index for the case of umbra and penumbra for the first time using the good data from IRIS. So this would provide us an opportunity to understand the importance of spatially resolved magnesium index on both the total and spectral irradiance studies. This can also be a foundation stone for understanding sun-climate relationship using SOOT on board Aditya L1. So with that, I'll be completing, and thank you once again for the opportunity.
Yeah, thanks, Megha, for this interesting talk. So we'll take questions from the in-house. In-person participant, please straight away ask your question.
The in-person participant, the host is actually not in the meeting.
Ah, okay, but okay, now we can then take some questions from the online participant. Whoever has question, please speak up. I don't see any raise hand, but you can straight away speak up. Yeah, your talk was very clear.
Maybe I spoke pretty fast. That
no, it was good.
Yeah,
speak nicely. Yeah, so thank you very much, Megha. I think we should move on to the next talk. So next talk is Soumya. Soumya Roy, are you there? Oh, Paul Rajaguru has a question, I guess. Paul Rajaguru.
No, I was just trying to point out that the Zoom has a problem for the in-person participants, I think. Do you have to wait for them, or you go ahead with now?
Well, I think so. I was, I mean, I got an email that we should finish all this talk by 6:30.
Yeah, fine. I was just saying, all those who are in the hall are not in the.
Yeah, exactly. So significant number of participants then are missing. So I can.
Yeah,
call,
okay, whatever the chat decides, we'll follow. Okay.
Yeah, I can call someone.
So it looks like it is a problem for all the parallel sessions. The whole Zoom is from the host side, from the in-person side, all Zoom sessions are out. Only who are completely online are still there.
Yeah.
So the next speaker is online.
So next speaker, Soumya, do you know Soumya is on
Soumya is attending offline.
offline? Okay.
So then you can't have them. No?
Yeah, and then I think the last speaker is Sudip, so he is in online.
Yeah.
Okay, yeah. Yeah, so we should wait for 2 minutes. That's what they're saying. They are really taking time.
So it looks like the hosts are able to connect now.
Yeah. So
we can't hear them yet.
yeah, they are now mute. Well, I guess, okay, still
So
the,
Megha, as a host, you can try to unmute them. You are the host, Megha, now. Megha Anand, if you are there, since you are the host, unless you unmute them, we won't be able to hear
Hello?
them.
Yeah, hi. Our internet is down here. So we are just creating a hotspot. So we are connected now. But I think Sudip, if you can make your presentation, I think that will be better. Sudip is online, yeah. Because
Okay.
the other talk is from here.
Right. No, I can do that. Yes.
Yeah. Co-host, yeah.
And also make
You just make X001 as co-host because you are the host now, Megha.
Okay. We can barely hear you guys.
Megha is the host. Megha can.
I cannot hear properly. Sorry.
So
Yeah,
they asked
Megha,
you to
you
make
can-
LHC 001 as the co-host.
Oh, I see. Okay.
this is very working.
Yeah, meanwhile, yeah. Should you can share your screen and start the presentation, yeah.
Okay.
Yeah, also.
Do you see the presentation?
yes, we see the presentation.
Shall I start?
Yeah, thank you, Sudip. Yeah, so please start.
Okay. Yeah. Okay. So good evening, good afternoon, everyone. So I'll be talking about observations from Solar Orbiter, a recently launched space satellite, and about campfires that has been the talk of the town from this instrument, a particular property of these campfire, and the work has been already published in the special edition of Astronomy and Astrophysics. So what are these campfires basically? These are very small scale, tiny, bright little. I see something come from behind, maybe. Okay. So these are small, little, tiny, bright structures that has been termed as campfires. And in one of these examples I show here on the left-hand side, that this is taken from the instrument called Extreme Ultraviolet Imager. There's a very small little brightening has been pointed out in this boxed region, and if you zoom it up on the right panel, you see that they are really, really tiny. Now we have to consider that scale of each of these pixels is as small as 200 kilometers. So these are 400 kilometers or so, very tiny in size. And if you look at their lifetime distribution, there also ranges from 10 seconds to 200 seconds. These are yet the smallest scale brightening observed in UV till now, and thanks to the spatial resolution of this instrument and the temporal one also. And in terms of temperature, they are million Kelvin plasma, from 1 to 1.6 million Kelvin or so. After the publication, after the announcement of these small little brightenings, there has been some simulation efforts also. One of them is this one from a Muram simulation, where they could simulate the small little structures along with all the other observed properties. I'll talk about this more in the later half of the slides. So what have we seen so far from this instrument is basically small little tiny brightness. There are a couple of instances where people have already seen jet-like structures, but the initial discovery of those campfires, they appeared like this over time. So you have small brightenings coming up and then going down, but there is no systematic movements. So since these are early days of these features, whatever we can gather will add up to our knowledge about these phenomena. So what basically in this work we are looking at is basically some of these campfires where it shows systematic propagations. So for this thing, I use the same data that has been used for the initial work, initial publication. This has these specifications which are absolutely mind-blowing numbers. So you have 200 kilometers spatial scale, cadence of only 5 seconds, which is fantastic given that we are looking for transients. And so this is a quite sun field of view, so not much activity, although there is some enhanced brightenings over here, and these boxes show where we see those events. So let's see how do they look. So I hope the movie is playing smoothly. So you see some of these brightenings actually move from one point to another, outlined by these boxed regions, where they show some systematic movements. In order to get some quantitative idea about them, we use the time distance diagrams. So these are some snapshots which will again give you a clear indication that over time they move from middle of the outlined box towards the one end and then go back. If you do a time distance analysis, I mean, if you create a time distance map, you get structure like this, where it shows that from one of the foot point, it rather bounces back. So we call these events, this type of events, as bifurcation events, because from the initial brightening, you see two slanted lines, which are basically indicating that it has bifurcated into two, and then one of them comes back. The other one do have a signature, but it's not really meaningful. So, and then this bouncing back, we call it as a reflection. If you see the speeds of these features, they are subsonic. So the sonic speed for a million Kelvin plasma is near about 150 kilometers, and they are really tiny, 20 or 50 odd kilometers. There's another exciting feature, is called simultaneous excitation. So if you look at the foot points of these so-called loop-like ends, and if you look at the light curves, these are the light curves. So you see that all the points actually show increasing trends from the start of this observation, even though we do not see any apparent brightening. So which is an indicator, which is an interesting, we do not really know how this can, I mean, how there are theories about small scale flux emergence or rogue polarities coming to the loop foot points, but there's no magnetic field information. So there is another type of case, bifurcation case, which is this one, where we see an initial brightening gets split into two, but this time the other splitted, the one moves almost vertical to the primary brightening, as you can see. So with these snapshots, the speeds are all, if you do the speed calculation, they remain to be the same. They are subsonic, and so they mostly grossly share similar properties. If you move on to, okay, now how we can explain these this reflection kind of a signature? One idea is to do via chromospheric evaporation, the classical picture which Fisher et al. Proposed. But then there is a doubt whether this small amount of energy deposition, can they excite chromospheric evaporation like what we see? There have been some studies with microflare-like events, but which could be possibly be working here also. But we are not sure, but looks like to be the most promising explanation. Let's look at another type where we see systematic movements, but in this case, we see that they are being merged. So there is already a stationary brightening outlined by this yellow circle, and then the red one moves and merged, and then the whole merged quantity moves back to the initial location. I draw a cartoon like this to illustrate the fact. And again, the velocities are subsonic. So that's an interesting feature. So let's look at another case, which we call it as multiple ejections. So we see that from one single structure, we have multiple slanted ridges corresponding to multiple brightenings propagating from one point to other point. And there is some interesting fact feature in this particular event, that you see that this line is slowly getting tapered off. In a time distance map, it means the velocity is slowly decreasing and it is decelerating. Now, whether this is a real effect or a geometrical effect in terms of line of sight effect, that cannot be established by this analysis. But the initial paper do propose, by Vaibhav et al., they do propose that these brightenings are actually happening in loops. The loops can have different shapes. They are, like these authors have outlined 4 cases where it can happen. And these are really low-lying loops as being done by Zhukov et al. By doing some triangulation techniques, and they come out with numbers like these are between 2000 and 4500 kilometers, the height of these loops, which is really, really low. So if you have these kind of geometry, panel B, then you can expect a deceleration because the loop is having this curvature. So this can be a line of sight, I mean a geometrical effect. Now, what about these are, as I have been saying from the beginning, these are smallest yet observed UV brightenings. How do they look with our known instrument and widely used? One of them is AIA. It stands for Atmospheric Imaging Assembly in a spacecraft named Solar Dynamics Observatory, SDO. It samples near about 400 kilometers, which is half the number which UI has observed. So as you can see, they are really, really fuzzy in AIA. And if you do the same analysis with them, you can hardly recognize if there is really a signal. So this particular event 4, you can see that once you have seen the UI maps, then only you can have an idea. Other than that, it's really difficult. So the point of showing this is to say that you couldn't have observed this with AIA, only you can do it with UI. So what we have learned from this study is we have learned that these reconnections are appearing either at the middle of the so-called loop, if we assume them as in happening in a loop, the loop apex or near the loop point. So this tells us about the reconnection location. That different kind of propagation tells us about the underlying magnetic field configuration, that because these plasmas are basically guided by the field lines, so wherever they go, they are tracing the field lines. So these different bifurcation things gives us an idea. And what we observed from our event is that there are not many within the field of view. That is an important, given that in terms of energy depositions, we always need many of these small scale events, but we do not see many of them. This could be a data bias because we have only analyzed one of these data. Could be, I mean, maybe they are there in other data sets all the time. So last a tiny bit about the magnetic structures. This was the simulation I showed you initially by Chen et al. So when they traced the field lines in the simulation, they could find these kind of field lines to be dominant where they see magnetic, where they see brightenings in their model. And now I have placed my event numbers over here in order to see that these kind of field line configuration can explain the bifurcation that we see in event 2, or even the reflection kind of signatures that we see in event 1. So what about the actual magnetic field information? So recently, after the publication of that paper of this work, there is a magnetograph instrument in the solar orbiter. It's called PHI. So it has provided the simultaneous magnetic field information at co-spatial and co-temporal magnetic field data. And this paper by Kahil et al. Analyzes those data, and they could see that well, some of these magnetic field, underlying magnetic field, do show similar kind of signatures what has been predicted by Chen et al. So you have the polarities, and if you hypothetically connect these lines, you can say that this is the place where these field lines are maybe reconnecting. So similar to this panel D. And there have been also been cases about small flux cancellation. Then there was one special case about flux emergence. So of course, this was only one data set with very few co-temporal images. So statistics is very poor. But we expect to get more of these data in coming days. And okay, of course, this is another information from Panesar et al., who analyzed the big looking campfires, which can be clearly resolved by AIA, and the conclusions remains the same, that they are there are a significant number of flux cancellation events, and there are very tiny bit amount flux emergence. So the last, what's next? When you observed all this, of course, the next bit is to go for spectroscopic data, because we already know many brightening events like bright points or UV bursts or explosive events, which are already known, small scale, tiny brightenings. Whether these campfires are different from them, or we are just looking the same stuff with high resolution instrument, that has to be confirmed with spectroscopic data. And of course, the more UI observations are needed with higher gradients. And when you go to 0.3 AU, solar weather goes to 0.3 AU, the resolution will be 3 times that of AIA. And we need to also look at active regions. This was all quite sun region observations. If we look at active regions, there has been a recent study by Tiwari et al. Using initial UI data from active regions, and they see dots. Whether those dots are the same as campfires or not, that needs to be established. So I will stop here, and thank you for listening.
Yeah, thank you, Sudip, for this nice talk, very informative. So I see Rayson from this elite. So I think they are facing problem. That's why they.
Maybe they can type in the chat.
Yeah. So they cannot unmute, but I don't know whether I can do it. I think Megha is
you can do it,
host.
You can just press on the button, ask to unmute.
I have done it. Isn't it working?
Yeah, because if I do it, it doesn't work. Okay, because I did it repeatedly. I think if Megha does it, then it may work.
Hello.
Okay.
Hello.
Now, yeah.
Okay, Sudip, this is Vaibhav. Thank you for a nice talk. Actually, we had internet connection, so I couldn't attend the entire thing, whatever you said. But I have one question. In 2016, we co-authored a paper where we found these propagating disturbances in XRT images, right? There also we had probably some sort of reconnection happening at 1 foot point, and these propagating disturbances getting some sort of reflection also. So my question to you is, this time you are saying that these are propagating campfire, not slow waves. Apart from these speeds that you get, I understand these are subsonic, but this could be projection effect also. So what is the difference between these and those events?
Okay.
Can you explain it?
Okay. That's a nice comparison. Yes. So the basic from physical point of view, as we know, the reconnections are scale invariant. So probably these are the same mechanism going on. We call it propagating campfires, but the campfires may not be a different beast. It may be the slow waves propagating from one part to another. So there is no way we can eliminate one or the other at this point of time. And my personal feeling is that these are the same UV transient that people have already been observed, like an UV burst, but we are just looking at with higher resolution. So once the spectroscopic data will come, this will settle. If we see a silicon,
we can look at spectral parameters then.
If we see a silicon profile getting two-sided lobes, then that will settle that okay, these are happening at this layer and all done and dusted. But we are still waiting for, because the campfires are small and you have to be really lucky to place your slit on top of a campfire. Yeah.
Okay, thank you. Do you have questions?
Yeah, do you have other questions?
Just a minute, actually, Dipankar.
Yeah, I just wanted to tell you, we are actually switching from one phone to another just to create a hotspot, because the internet connectivity in IIT Roorkee is completely down. So we will continue and try this. If there is online questions, please take that now.
Okay.
Yeah, do you have any questions from the online participant? I don't see any raise hand. Yeah. Yeah, Jayati. So I think I need, okay. Vibhuti was saying that I need to co-host Jayati.
No, it's okay. Is the file copied here? The next presentation, Jyoti? Okay. So we'll try to
stop sharing.
You can stop sharing. Yeah.
Okay. Thank you. Thank you.
Yeah. Thank you, Sudip, for this nice one. Thank you.
So we'll try to share from this.
Yeah.
I hope you can see the screen now, right?
Yeah, it's perfect.
Okay. Yeah.
Perfect. Yeah, Soumya, please start.
Yeah, so good afternoon, everyone. And today I'm going to take you through some of the work that I have been doing regarding the forward modeling for the Solar Ultraviolet Imaging Telescope. So for the sake of completeness, SUIT is one of the 7 payloads on board the Aditya L1 mission, upcoming Aditya L1 mission. It's an imaging telescope which will provide both full and partial disk images of the sun in the 200 to 400 nanometer wavelength regime. It has 11 science filters and a pixel size of about 0.7 arcsecond. So on the top right hand side, you can see the schematic diagram of the payload itself, and down here the details of the 11 science filters. So we have quite a few interesting science filters here. So for example, the narrowband 3 and 4, they specifically look at the magnesium 2 H and K indexes. The narrowband 2 and 5 look at the wings of the magnesium 2 lines, and the 3 broadband filters 1, 2, and 3. Together, the 3 of them observe the continuum in the 200 to 400 nanometer region, the whole 200 to 400 nanometer region, which would in principle allow us to attack questions like sun-earth climate connections directly, because we are observing the whole continuum emission in that region. So the main questions SUIT aims to address are the following: the magnetic coupling and dynamics of the solar atmosphere, the spectral energy distribution in solar flares in the near ultraviolet regime. And it also has the capability, because it can image the whole sun, it also has the capability to monitor and measure the spatially resolved solar spectral irradiance in the near ultraviolet regime. So the work that I have been doing is to try and forward model mock SUIT observations. For creating the flux maps, I have been using the MPS Atlas simulation. So it is essentially an updated version of the well-established Atlas 9 code, which is generally widely used for atmospheric modeling and stellar spectral synthesis. So given any hydrodynamical simulation cubes, it can solve radiative transfer through that in local thermodynamical equilibrium using the ODF method. So for our purpose, we use pre-simulated Muram cubes to create synthetic observations. The good thing about the updated version of the Atlas 9 code, the MPS Atlas simulation, is that it can be used for any arbitrary filter profiles. So how it helps us in our case is we directly use measured SUIT science filter profiles to solve the radiative transfer through them, so that we have to incorporate the effects of the science filters directly into our calculation. And as you can see on the right hand side, we can have a cube like this, and we can slice them up on various angles and interpolate them to also add the effects of the line of sight that you're observing the cubes in. So
It's frozen again.
Yes.
Currently.
It's really surprising. The whole thing went down.
can you hear me?
Yes.
Okay. Share your screen.
Okay, perfect.
So, yeah. So in principle, you would get spectra from each of these points, which you can then integrate and add along the whatever line of sight one is trying to simulate, and end up with flux maps like this. In this particular case, this map is 6.6 arcsecond in both direction. Then we stitch these maps up, multiple of these maps up, to get a larger map, so that when we try to convolve with the suit, इसमें तो कनेक्शन नहीं है, बस स्क्रीन दिख रहा है, जूम चल रहा है अभी भी, पर यहाँ पे कनेक्शन नहीं है। Oh.
We can hear you, I think. What is the issue?
Sudipta, can you hear us?
Yeah, clearly.
Okay, I think then it's not showing,
Okay,
but it's
yeah.
The session will auto switch to the Ethernet line.
Yes. It is not showing it connected to internet, but it is working.
Yeah.
So you can still see my slides, right?
Again, I have the control and can
Yes,
see
indeed.
your slide.
We can see your slides. We can hear you clearly.
Okay. Yeah. So we stitch these maps up so that the angular scales become comparable with the suit PSF that we have. Currently, the characterization for the suit PSF is going on in the labs. Throughout this work, we have used the modeled PSF. So the suit field of view is about 0.75 degrees in both direction, and the PSF is modeled in 25 independent patches. So each of these patches is about 0.15 degree, and the response you see in each of these patches is actually the PSF that represents the PSF that is represented for that each of those individual patches. So what one has to do is you have to know where the cube that you're trying to convolve is going to fall on the whole FOV, and according to that you have to pick up the PSF patch and convolve with that. So here I am showing you the convolution of this map with the central PSF, and this is what you end up. And after that, you have to rebin the whole convolved map to the suit plate scales, simply because the Muram simulations that we are using are on much higher resolution than what suit can observe. So finally, you end up with mock simulated observations for suit. So the very next thing that we had to do was try and see what happens, how the performance of the PSF affects the observations, is going to affect the observation. Because if you look at the PSF models, as you go from center to farther away towards the edges of the field of view, of course, the imaging performance is going to get worse. So here you see one such example. We take this 33 arcsecond map and we convolve and ribbon them with various patches of the PSF. So this shows the central part, how this map is going to be observed. And then we progressively move to 0.15, 0.15 and 0.3. So essentially moving towards the edge of the PSF along this diagonal. And as you can clearly see towards the edge, at the furthermost point, the imaging performance is very bad. Not that we expect that any part of the sun is going to be falling on that patch unless there is a huge pointing error. But just for the sake of completeness, we anyway do the characterizations. So here is how we try to quantify how the contrast is going to look like. So essentially, you can pick up some line along the simulated flux maps and look at how the contrast is varying. So the four figures here show the contrast maps for 4 different line of sight observations. The blue one in all of these cases is the original contrast in the Muram simulated cube. And the 3 other ones, the orange, green, and red, is what you end up with after you convolve and ribbon them to suit plate scales. for various patches of the PSF. One of the first things you can notice is all the high frequency structures are washed away completely, which is again what you would observe because of the difference in the resolution from simulation and what suit observes. And also the other thing to look at is the cornermost patch, that is the worst part of the PSF, actually washes out a lot more. The peaks start appearing in different places, which is again what you would expect. So this here shows a simulated map of how suit is going to observe the sun. So what essentially you have done here is you have taken such simulated map and convert them with various parts of the PSF and stitch them up. So here you can see the effect of limb darkening clearly visible. This calculation has been done with steps of mu equals 0.1. And as I was telling earlier, we don't expect any part of the sun to fall on the cornermost patches of the PSF unless there is a huge pointing error. One other thing the MPS Atlas simulation actually helps us is to constrain the behavior of the observed flux outside that of the passbands. So for example, here you see the broadband 3 filter profile, and we have some predetermined band values present. So we call this region in band. This is for broadband 320 to 360 nanometer. And we wanted to quantify how much flux we get outside of this passband. And that is important for two main reasons. One thing is that because it essentially helps us to select the science filter profiles that are going to be mounted in the payload itself, because so that is one of our selection criteria, the amount of leakage. Where you see the least amount of leakage, we decide to mount them in the actual payload itself. And one of the other reasons is that although we have some predetermined passbands present, we want to give the community the ability to choose their own passbands depending on what kind of science they're doing. So one of the key concern there was, if someone changes the passband, how does that affect the contrast that you observe? So that is essentially what we have done here. All these three figures again convolved with the central patch and then along the diagonal. And then these curves here show the passband that has been taken from the broadband 2 filter profile. And as you can see, one of the good thing about that is, so 254 to 300 nanometer is the original decided passband that the suit team is using right now. But if you go beyond that, the contrast doesn't change much, which means that the assumption we were working on, that the passband that we had chosen beyond that the flux isn't going to be contributing much, is true. But if you start cutting down into the passband, you can see that the flux starts dropping in the comparatively low brightness regions. So we are currently going through the studies of this, depending on where we chop off, how the contrast starts varying. So that finally, when someone wants to decide on any kind of passbands they choose, they would have that information from us. The next thing is we are trying to see how good suit can observe various stuff. So essentially, we took various existing IRIS SGI observations and convolved them with the suit PSF. So on the top panel, you can see X-class flare happening in IRIS SGI, and in the bottom panel, the same thing, convolved and rebuilt to suit plate scale. If you take these two lines, the horizontal and vertical line, I again show the normalized intensity variation along that line. So in both of these figures, this is the vertical and this is the horizontal. The blue one is the original intensity variation that you see from the IRIS SGI observation. And the three other lines, the orange, green, and the magenta, are again three patches convolved with the suit PSF. And as you can see, the contrast variation is reproduced quite well enough. And same again for an active region. Here also the same thing. The IRIS observation, the bottom panel is convolved and bent to suit PSF suit plate scale. And again, here the vertical and horizontal line, the blue one is the original from the IRIS SGI, and the three other ones are the contrast variation that suit is going to observe, which is again very well reproduced. So finally, the last thing that I have been working on for some time now is deconvolution. So here you can see again the same stitched flux map and the suit PSF model. So if somehow this ends up on the cornermost patch of the field of view, this is the flux map that you produce after the convolution. Now our point was, if we can deconvolve and recover the initial flux map that has gone into the convolution. So for that, we are using the well-known Richardson-Lucy deconvolution algorithm. I wouldn't go into much details of it, but it's one of the well-known algorithms for deconvolving observations where the PSF is known. And since our case, the PSF is modeled PSF, we know it very well enough. It has been used extensively in many imaging telescopes like AIA and HST. So as you can see, again, from the same deconvolved map, we can recover a flux map like this. It will, as I mentioned earlier, it will be mostly be useful for deconvolving observations from the edges of the PSF. So to quantify how the deconvolution algorithm actually performs, here I show a normalized distribution of the deviation from the original image divided by the original image. So this is essentially a percentage deviation. As you can see, most of the pixels actually fall between plus minus 20% deviation, which is not good enough at all. So anything related to photometry probably will have to do much more work. It's still not going to be science worthy if you deconvolve the observations using the algorithm. But if you look at the intensity maps, how the contrasts are reproduced, so the orange line is actually the convolved map, and the black line is the original contrast variation you had started with from the simulation. And as you can see, because of the distortion by the PSF, the peaks had moved around. And the blue one is what we recover after the deconvolution has taken place. So we actually recover quite a bit of the peaks from the original flux maps. So right now, as it stands for this deconvolution pipeline, because the flux is not locally conserved, it won't be very useful for any particular science cases where you have to use photometry. But if you're trying to track a transient event, you want to know its location on the sun's surface very well enough, it's still going to be quite useful. So this is where I would wrap up. This is the current status of all the things. So an end-to-end pipeline is in place for simulating soot observations using Muram cubes, which can help us creating a batch of flux simulated observations for soot before even it starts observing. So we would have an idea of what soot is going to observe and shape our science questions according to them. A preliminary version of the deconvolution pipeline is in place, although like I mentioned, it's still not good enough to do any photometry based science. Tests for absolute calibration scheme, that is given the count you want to know the energy, is still going on. And science filters that are to be mounted on the payload is already selected, and the science team are actually testing them right now in the laboratories. So thank you. Yeah, Sudip.
Okay, nice talk, Soumya. So I have two quick questions. One is regarding the Richardson-Lucy deconvolution. So one of the problems about deconvolution algorithms in general is to know when to stop, because you keep on iterating and then at some point in time you just add noise to the image. So do you have any handle on this? And
so
I will,
the way,
sorry,
yeah. So the way I'm doing it is I am looking at the difference, the amount of change between two successive iterations. And if that converges, I stop. But like I said, it's still in very initial stages, this deconvolution pipeline. I might come up with something else. But right now I'm doing that. I'm looking at how the difference changes between two successive iterations. Yeah.
Okay. And another quick question is that you talked about the change in contrast, a change in contrast as you change the band pass. What about the sharpness of the image?
So how would you define the sharpness of the image? I mean, like quantitatively, i.e.
You can take, I don't know, maybe radians or something. I have no idea.
So what essentially I'm showing is how in any of these images, how it is essentially the normalized intensity along that line. So this tells you how much intensity difference you see from the darkest point to the brightest point. And I think that is something like sharpness.
You take the gradient.
Okay.
Okay. Yeah, you can take the gradient of that. But I haven't looked at the gradient of the intensities, so I don't know how that changes.
Thank you.
Nagaraj, you have question? Yeah, please speak.
Hi, it was nice talk, nice work. So I wonder, there are like, bright, when you do the convolution, you
Right.
see bright points, like, we see in kind of crystallographic structures. Why is it an artifact while doing the convolution?
Which one are you talking about? This image or?
Flash one of these convolved images from Muram.
So are you talking about these?
Previous one. Here, see. Okay, these are when you do the convolution. See, you start to see a lot of bright points, kind of thing. I mean, we see these kind of things in high resolution, of course. Just I wonder how this happens.
So are you talking about these points?
Yeah, that one, right? Yeah, those.
Yeah, that is definitely an artifact of the convolution, because essentially every time you do a convolution, you're doing a Fourier transform. So you lose some information in space because you lose some pixels every time you do the convolution. So the flux actually gets concentrated in a smaller region. That is one of the known artifacts of at least what I'm using right now to convert.
Kind of edge smoothing while doing the Fourier
So I tried padding, but the problem with that is that essentially introduces a lot of false pixels at the edges, which becomes problematic when I try to do the deconvolution, because then you have a very sharp gradient where the padding has gone in the intensity, and the deconvolution algorithm can't handle that. You can try do padding, but then essentially where you do the padding to keep the shape same, it introduces a very high intensity gradient. Of course, in the original observations that won't be there, but I can't handle them in my computation. So I just haven't done padding.
Okay, maybe we'll discuss after some.
Yeah, sure.
Yeah. Okay, thank you.
Any other questions?
Yeah, someone here has a question.
I have a very basic question about forward modeling. So as we do forward modeling of optically thin channels, so there is line of sight integration in that. So how forward modeling works in this case for magnesium lines? Because
magnesium lines, I haven't done the forward modeling.
No, so you have shown some pass band. So
yeah, so essentially for the magnesium channels, the narrowband 3 and 4, I haven't done any forward modeling.
So have you done the forward modeling for optically thin channel or optically thin channel?
Optically thin channels.
Optically.
Yeah.
Okay. Thank you.
Okay, then I think if we don't have any other questions, we can close the session. So thank you very much, Soumya, for the talk, and I thank all the speakers in this session for giving interesting talk, and all the participants who were present and asking for interesting questions. So thank you all. I guess there is no announcement, and I'll leave then.